Now, in a previous lecture, we have learnt about centripetal acceleration in uniform circular motion. We have also learnt uniform circular motion means the speed of the particle remains constant while moving in a circle. And you see that there is only one acceleration in such a motion, that's centripetal acceleration. As the name suggests, this acceleration is pointing towards center of the circle. Now the question comes, if the circular motion was non-uniform, that is the speed also changes as the particle moves in the circle, then what would be its acceleration or accelerations? If you look at the headline there, it points out, it signifies that if the circular motion is non-uniform, we can expect two accelerations. First of all, why? And let us consider a few basic questions. First of all, we know that velocity is a vector quantity. It has got a magnitude and a direction. See, velocity is changing, not constant. It might have many different meanings, as we can see here first. You can see I have just considered the first simple case where a body is moving in a straight line. That is the case. Here is the block, you can see, and its initial position is here and finally it's here. And suppose initially its velocity is given by this green arrow to the right, that was v1 at time t1, and later the velocity has increased to v2 while keeping the same direction. Now we can just call this is the origin here, and this is my plus x direction. So we see that the velocity vector that in the first case maybe initial time was t1, it is v1, and then it's become v2. This v1 and v2 are different vectors because they have different magnitudes. Different magnitudes. So what we mean here is that the magnitude of v1 and magnitude of v2, they are not same, while they have the same direction to the right along plus x axis. Now here also a case we can see velocity is varying, but that's only because magnitude is changing but direction is remaining constant. Now when the particle has the same direction of motion, that is velocity direction remains intact, then we call that is straight line motion, as you can see here, and accordingly there is an acceleration as well. This will be using just red arrow for that, and let me call this as a, and this a is coming in the picture because the velocity has changed in magnitude but not in direction. Direction is constant. This is direction same. So whenever a particle has got its velocity changing in magnitude but direction remaining same, that becomes a simple case of accelerated motion in a straight line, as we have seen first. Next, we shall go for the case where the speed is remaining constant, that's magnitude is remaining constant, but direction is changing. And for that, we shall recall the case of uniform circular motion. So let me construct this figure here. Now this you can recognize to be the case of uniform circular motion. This white line is the circular motion shown. This is center of the circle. And these green arrows, this is v1, v2, v3, v4 in all four locations. They are the velocity vectors at different locations. So let me just name them. These are v1, let me call them v1, v2, v3, and v4. I just show four of them at four different locations. And you'll agree that while in uniform circular motion, these magnitudes of these v1, v2, v3, v4 are the same. So you could write down that this is v1, v2, v3, v4. They are all same magnitude because I didn't put the arrow symbol, and they are all equal to v, the constant linear speed of circular motion. But as you can see, as the motion is in a curve on a plane, continually you can find direction of velocity vector by drawing tangent at the point to the circle where the particle is. So when the particle is here, you've drawn a tangent to find direction of v1. and so on. And you can see everywhere as the particle moves in a circle, directions of v keeps on changing along the tangent. So here is the case where you found magnitude is different. Magnitude remains same magnitude, that is. In uniform circular motion, the velocity vector, this was my case number 1, that was straight line motion. This is my case number 2, uniform circular motion, that is same magnitude of velocity vector, but different directions, as the figure shows, different directions, as direction of the velocity vector is along the tangent drawn to the circle at that particular position. So that was the case. Here again we find the velocity vector is changing, but here it is because of change in direction while magnitude remains same. Previous case was magnitude was different, direction remains same. So in my third case, we shall consider a more complicated situation where the motion is in a circle and where the speed is also changing. So that's my next situation. So you have the third figure on your screen, as you can see it here, third case, but I shall be confining myself to the second case for a few more moments. See, I missed out on one thing. Look at these red arrows here. They are standing for the corresponding acceleration, because since v is changing, and that's because of change in directions. Here is a unusual case where the magnitude remains same, but direction was changing, and because of the change in direction, velocity vector was changing. And if v vector is changing, acceleration must be here. And you have learned in a separate lecture that this acceleration is known as centripetal acceleration, AR. R is standing for the word radial. It's radially inward. So you see that if I show this AR, the radial or centripetal acceleration in all the 4 cases, they're given by the red arrows. And as you can see, that in each case it's pointing towards center of the circle. That's why it's called centripetal, center seeking. Now, you are also aware the value of AR has been proved to be v square by r, where v is the constant speed of uniform circular motion and r is the radius of the circle. So since the value of v is remaining constant in uniform circular motion, and of course r is constant, we can conclude that in the second case, in uniform circular motion, where speed remains constant, the value of AR, that is centripetal acceleration's magnitude, remains constant everywhere on the circular path. That's why you find these red arrows have the same length everywhere, but their directions keep on changing since it's pointing towards center. As you can easily argue, at different locations, the direction is obviously changing because it has to be towards center at every single location that's radially inward. So in uniform circular motion, centripetal acceleration is the only acceleration given by AR which has got a constant magnitude depending on speed and radius, but variable directions along the inward radius. With this we come to the third case. Now that's, I have said, a little more complicated situation, and we call it non-uniform circular motion. Now what does it mean? Let me first show these velocity vectors, the green arrows, and I am calling them v1, v2, v3 and v4. As usual, we could have drawn more arrows, but I have chosen any 4 of them, any 4 arbitrary locations. So see, here it might happen. Not only the direction is changing, quite obvious, because in circular motion, since along the tangent direction of velocity is, so v1, v2, v3, v4, they all have different directions along the tangent. But here one more thing, even the magnitudes of these velocity vectors are taken to be different. So that's the difference between uniform circular motion and non-uniform circular motion. In non-uniform one, the last one I'm discussing, here velocity vector is changing not only in direction, that's obvious, it's also changing in magnitude, and hence we have chosen different lengths of the arrows. You can see the green arrows. In my case, I have taken them of increasing length, so they have got different values. And correspondingly, you must note here. So let me write what I say. Here we have got different.
Hello students, you got a glimpse of our video lessons through this small lecture. We have hundreds of lectures like this one covering various topics of advanced school level and intermediate physics in our website. They are exhaustive and often accompanied by elaborate diagrams to make concepts even clearer. They are taught with passion and sometimes with a bit of fun. So, at the end of the lesson, you have a commanding grip on the subject and you are ready for the board and competitive exams. Subscribe at physicsacademyonline.com to access video lectures of highest standard on various topics of physics.